I hope recording is started. Hello everyone. Today lectures will be dedicated to unsupervised learning, semi-supervised learning, and clustering. If you have any questions through the lecture, please write them in the chat. I'll try not to miss them and respond because I have some issues with my speakers on laptop. So yeah, I might not hear the questions here. That's it. I think we can start. Well, in classification tasks, we deal with learning a mapping from a set of objects to a finite set of class labels. The classes are predefined, meaning that from the beginning, we have a general understanding of the nature of each class, and we have access to a training data set. Yep. Training data set with some examples of objects and their corresponding class labels. In clustering, we're also partitioning objects in a finite set of groups, but we don't have a training data set or prior knowledge of what these groups will be. The fact that a clustering model considers certain objects similar and assigns them to the same clusters is a new information as an insight discovered by a model itself. Since we don't know in advance what the clusters will be or even how many of them there will be, clustering is a unsupervised learning task. Due to the similarity with in problem formulations, clustering is sometimes referred to like unsupervised like classification in the literature. Also, clustering methods are often used when we essentially need to solve a classification problem, but collecting a labeled training data set is difficult or costly or time consuming. However, gathering is much easier as it requires fewer labeled examples. That said, it's important to remember that the accuracy of supervised methods is significantly higher. Therefore, if it's possible to collect a labeled data set, it's generally preferable to solve the classification problem rather than rely on clustering. So this is a overview of our today's lecture. So let's talk about the problem statement. The task of clustering, or as we know, unsupervised learning, is formulated as follows. Given a training data set, XL, which is equals set of X1, blah, 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 XL, and which subset of some space of objects X, and the distance function between objects, some, for example, row. The goal is to partition the dataset into disjoint subsets called clusters, such that each cluster consists of objects that are close to each other according to the metric rho. While objects from different clusters are significantly distinct, each object X in Excel is assigned a cluster label, Y. So we have only X's, and we want to give them new labels, Y, with the same distance, something like this. A clustering algorithm is a function. For example, here is A. From X to Y, that assigns a cluster label Y small in Y big, to any object X small in X big. In some cases, the set of labels Y is known in advance, but more often the problem involves determining the optimal number of clusters based on specific clustering quality criterion. The solution to the clustering problem is inherently ambiguous for several reasons. First, there is no single base criterion for evaluating clustering quality. There are many reasonable criteria in various algorithms that don't have a strictly defined criterion, but still produce fairly reasonable clustering, like by construction. Also, these different approaches can yield varying results. Second, the number of clusters is usually unknown in advance, and it's determined based on certain subjective criteria. And the last, the clustering outcome heavily depends on the metric rho, which is typically chosen subjectively and defined by some expert. Oh, here I missed image, but there should be like a difference, the same sets, but differently colored. So there are a different number of clusters on the image. Also, clustering differs from classification in the fact that the labels y, if of the original objects are not predefined. And even the set y big itself may be unknown. In this sense, the clustering problem is even more ill-posed than the classification problem. Clustering goals may vary depending on the specific application of the task. First of all, to simplify further data processing, partitioning the set XL into a smaller group of similar objects to work with each group separately. For example, classification, regression, or for a prediction task. Also, to reduce the volume of stored data, retaining only one representative per cluster, like data compression task. To identify atypical objects that do not fit into any cluster. For example, one class classification task. And to build a hierarchy of object sets, taxonomy task. In the first case, the goal is to minimize the number of clusters while ensuring a high degree of similarity among objects within each cluster. In the second case, the priority is reducing data storage, and the number of clusters can be arbitrary. In the third case, the main interest lies in identifying outliers that don't fit into any clusters. In all these cases, hierarchical clustering can be applied, where large clusters are divided in smaller one, which in turn can be further subdivided, and so on. These tasks are referred to as like taxonomy tasks. And the result of taxonomy is not just partitioning objects into clusters, but tree-like hierarchical structure instead of single cluster number. An object is characterized by a list of all clusters it belongs to, and from the largest to smallest. A classic example of taxonomy based on similarity is the classification of living organism proposed by Carl Linnaeus. I don't remember, in the mid-18th century. In modern biology, the taxonomic hierarchy has around 30 levels, with several considered primary, like kingdoms, phylum, class, order, family, and so on. Taxonomy is widely used in various fields of knowledge to organize information about large datasets. We'll focus on the hierarchical clustering algorithms later that allows for hierarchical data representation and optimize that data processing. Let's try to compile a registry of different types of cluster structure that may arise in practical tasks. So it's densifications. It's some inter-cluster distance are generally smaller than inter-cluster distance. For example, social network communities, group of people with a strong internal connections, for example, friend circles, but weak connections to other groups. Like it may be several friend groups from different countries that have nothing in common, but they exist standalone. Also, it may be stripes, or another name is elongated clusters for any object. Yeah, here. Yeah. For any object, there exists a nearby object from the same cluster, yet some objects in the clusters that are not close to each other. For example, it may be traffic flow on highways, vehicles moving in a continuous but structured manner, forming elongated pattern of congestion. And this example cluster with a center, in each cluster, there are an object such that almost all objects in the class lies within a sphere centered about it. For example, city districts. So yeah, many tasks in clusterization have the similar vision and similar visualization of it. Yeah, and it may be depends on each other. Another is clusters connected by bridges. So cluster may be linked by some connections, which complicates the work of many clustering algorithms. Different research fields, like if we want to say clusters, may have a few interdisciplinary studies that act as bridges between them. For example, if we have computer science, maths, and physics, they have small, different small connections between them. Also, clusters on a sparse background. Clusters may overlap with a sparse background of rare RCP object. For example, stars in a galaxy. Stars clusters exist, but are surrounded by a sparse background of isolated stars that are not in the same galaxy. Also, we can talk about overlapping clusters. Some clusters may partially fully overlap with one another. For example, music genres. Songs may belong to multiple genres in the same time. For example, jazz, fusion, electropop, punk rock, or some other music genres. And clusters may be based on unknown properties. Cluster may form based on unknown predefined properties rather than similarity. Standard clustering methods fail in this case. Customers, for example, customers group may form based on hidden psychological factors rather than visible demographics. And we can have no clusters at all. If clusters don't exist in the data, clustering should not be applied, and other data analysis methods should be used. When data doesn't naturally group, the clustering is ineffective, and statistical analysis may be a better approach. Different clustering algorithms may be more or less successful in various situations. Simple algorithms are usually highly specialized and provide adequate results in only one or two scenarios. More complex algorithms like Farrell or Lance-Williams agglomerative procedure, which we talk later, can handle multiple types of situations. However, designing an algorithm that works successfully in all cases without exceptions is very challenging and hardly solvable task. Another reason why the clustering problem can be ill-posed is its sensitivity to the choice of metric. I took this image from old Soviet era textbook, but it's good image and very informative, even if you don't understand Russian words. Yeah. In the example, we have a group of students which was analyzed with their weight in kilograms and height in centimeters. On the other way, when the data points were plotted, the cluster seems intuitive. So female students, this not one. Female students formed one cluster, A, and B, male students formed another. However, when the horizontal axis, which weight, was scaled down by factor 1.5, the metric changed. Technically, it remained the same Euclidean metric, but now one of the features was given 1.5 times less weight. As a result, the clustering interpretation completely changed. Instead of distinguishing male and female students, the new clusters identified tall boys as one group and everyone else as another. This demonstrates how clustering results depend entirely on the choice of metric. However, for the sake of the discussion, we will assume that some reasonable and correct metric had been provided to us by someone higher authority, and we will not question about it. If the metric changes, the clustering results will change as well. So, a bit about the second problem formulation. I will often discuss both problem formulations in parallel because many methods can be easily adapted to this second approach by adding or editing just one line of code. And the algorithm will be totally the same. We call it semi-supervised learning or partial learning. The key idea is that we may have a large number of unlabeled objects, but for a smaller subset, we have access to the class or cluster labels. It's not always clear whether to call them classes or clusters, but this problem is generally closer to classification because we have a predefined set of possible labels, some like finite set Y. And even if it's small and still represent a well-defined category system. There are several variations of this problem formulation with subtle terminological differences. One important distinction is between semi-supervised learning and transductive learning. So semi-supervised learning, when given an object X, and the goal is to predict X class membership, as is in unsupervised learning. And transductive learning, this differs from the both induction, like transductive induction and deduction. So induction is generalizing from the specific instances to general rules, and deduction another way. Applying general rules to specific cases. And in fact, all of machine learning is sometimes referred to as empirical inductive because we derive a general mapping function from the dataset. However, transaction is neither induction nor deduction. Instead, it involves mapping from the specific instances to other specific instances. That is, we already know the full set of objects where labeled are missing, and our task is to infer those missing labels. The predefined set of objects directly connects transductive learning to clustering, as we have complete knowledge of the entire unlabeled dataset. And this global knowledge can help us in classification or clusterization. The key characteristic of transductive is that no new objects will appear. We only need to label the existing unlabeled instances, making it a closed set problem. So, for example, in semi-supervised learning, the dataset may grow, and maybe there may be some different objects. But in inductive learning, we have data set and we never change it. Semi-supervised learning is widely used in tasks where labeled data is scarce, but unlabeled. Data is abundant. For example, in healthcare, SL helps classify medical images like MRI scans with a minimal expert labeled data. In speech recognition, it improves transcription models by leveraging a vast amount of raw audio. Fraud detection benefits from SL by identifying suspicious transactions with a few labeled fraud cases. Many social media moderation uses SL to detect harmful content with a limited human annotated post. There is a question. Do we have a labeled dataset? We have a small part of our dataset that's labeled. So, like here, we have some set of object X and classes Y, and we have the big amount of objects that was enabled and like in previous. Yes, but when we talk about semi-supervised learning, it often uses the unsupervised training algorithm. So we don't need this labeled data as much as in many supervised learning. So this training data, this labeled data set, labeled data just will help us, but we will still use unsupervised learning methods. So yeah, supervised and unsupervised have different approaches for learning. So use. Yeah, we can use it. For example, if we have this in labeled data, we have some classes, so we can refer them. Like we know classes, we know some example which corresponding with the objects, and we just need to correspond other objects which are unlabeled to our known labels. Because in the pure unsupervised learning, we may not know even the number of what are the labels. And here we have some like hints from dataset. Super. What else about tasks? For example, in autonomous driving, SL enables like safe driving cars to recognize road objects without fully labeled datasets. It helps, for example, in cases when car maybe goes on the road on which never was before. Yeah. For example, also drug discovery utilizes SL to predict effective molecules based on the smaller set of tested drugs. And finally, OCR, optical character recognition, as I remember. Systems leverage SL to improve handwriting recognitions with a mix of labeled and unlabeled scanned documents. So let's consider a case where we have two Gaussian distributions with the same variance. According to Bayesian classification theory, which I hope you had in the previous semester, which the optimal decision boundary between these distributions should be linear, like one line. However, if we have only received a smaller labeled data set, say we have labeled samples from each distribution, for example, 5, this information may be insufficient to recognize that the data comes from the two spherical Gaussians distribution. As a result, the classifier might fit a highly non-optimal quadratic decision boundary, which don't accurately separate the two distributions. This information is not necessary. It just shows that SL is not just classification task. Now, if we are also given a larger set of unlabeled data, we could recover the true mixture of Gaussians, recognize that the data belongs to two components, and correctly apply the Bayesian classifier. This would allow us to construct the correct linear decision boundary as expected from Bayes' theorem. So this is a perfect example of how semi-supervised learning improves classification by leveraging unlabeled data to reconstruct the true data distributions. This is a classical example demonstrating the power of semi-supervised learning in the two moons or two bananas. In other words, problem. This problem consists of two intertwined clusters that it is visually clear, here, two clusters. It's visually clear that they should be separated along in a curve boundary, something like this. However, if we are given only a few small labeled data set, for example, just these points, per cluster, traditional supervised learning methods such as KNN or decision trees or any linear classifier will struggle to find a meaningful decision boundary due to the lack of sufficient label data. For example, if we have some linear regression, or some linear methods classifier, the classified boundary will be like here, and it's not good for us. However, if we approach the problem using clustering, we can first identify the two natural clusters of the data based in this structure. Once the clusters are detected, even with just one labeled point per cluster, we can assign labels to the entire dataset. This allows us to successfully classify all points, demonstrating how unlabeled data can help define a complex decision boundary that purely supervised methods would fail to capture with limited labels. This situation in semi-supervised learning is fundamentally different from clustering. And the two cannot always be reduced to one other. The key difference that in SL, the labeled data points provided by the teacher take priority over the natural clustering structure of the data. For example, we had this labeled data, and we should think that it's always true. It cannot fail. Maybe in some algorithms it may, but we don't talk about. Imagine a case where we apply a SAL of the two moons to bananas problem. Suppose a teacher provide a few label points, assign 1 point from the lower banana to the same class as the upper one. Despite the natural clustering structure suggesting that the lower banana should remain a single cluster, the fact that a teacher labeled two distinct points as belonging to the same class forces the SL model to split the lower banana into two separate parts. Even if it contradicts intuition clustering methods or any unsupervised structure in the data. This demonstrates the unique nature of a SAL, which sits between classification and clustering. Unlike pure clustering, where data structure dictates the groups, and unlike pure supervised learning, where a full dataset is labeled, a SAL must balance between trusting the given labels and utilizing the inherent data structure. This makes a SAL is a tricky hybrid problem that requires careful handling. Yeah, I'll take that everything is recording. Yep, I hope it's recording here as well. Okay. All right. So far, we have discussed the problem formulation, and we'll continue to consider both approaches, clustering and semi-supervised learning side by side. The reason is that many clustering algorithms can be adapted to a cell with just a small modification, often changing a single line, as I told before. In the final part of the lecture, we'll do the reverse, take some classification algorithms and adapt them to semi-supervised learning. However, this procedure is much more challenging, but it was some little spoiler. A fundamental question arises: how do we measure clustering quality? Can we define clustering as an optimization problem? The answer is yes, but there are multiple possible ways to do it. One of the most commonly used methods is to compare intra-cluster and inter-cluster distance. So intra-cluster distance compute the average distance between all pairs of points within the same class. So it's just counting distances inside cluster. And on the other hand, inter-cluster distance compute the average distance between all pairs of points from the different classes. Once we have these two metrics, we can combine them in different ways. For example, by taking the ratio, calculating the difference, or applying other statistical measures. A major disadvantage of this approach is that it required pairwise comparison of all objects in our dataset. leading to quadrical complexity big O from n square, which becomes infeasible for a large data set. Can we do it some maybe faster? So yes, if a clustering algorithm computes clustered centers, for example, new y for each cluster y in big Y, we can define more computationally efficient functionals to evaluate clustering quality. For example, we can minimizing intra-cluster distance to ensure that objects within the same cluster are as close as possible. We minimize the sum of squared intra-cluster distances. Here, we have a representation of class, center of class mu, and rho is our distance metric. If rho is Euclidean, then phi O has a physical interpretation. It represents the moment of inertia of a cluster treated as a mass system where each data points have equal mass. So it's just some amount of balls that have their corresponding inertia. Also, we may maximizing inter-cluster distance to ensure that different clusters are as far apart as possible. So we, in first case, we minimizing their inside distances, and the second, we maximizing the distances between the different clusters. So we, not clusters, but we maximize the sum of squared distances between each cluster center and the global center. Yeah, and we can combine both criteria like in previous. In practice, we need a balance between compact intra-cluster distance and well-separated clusters. This is done by minimizing the ratio of difference between the two functionals. This approach ensures that clusters are internally tied while also being externally clustering quality. Yeah, now let's discuss one of the most widely used methods for evaluating cluster quality, the silhouette coefficient. This measure provides a way to assess how well defined the clusters are and how well individual points fit into their assigned clusters. Explanation of this. The silhouette coefficient is based on the comparing two distances of each point in data set. Its average inter-cluster distance, R little. This measures how close a point in the other points within the same cluster as before. And average nearest clusters distance, big R. This measures the distance from the point to the nearest other cluster. A higher value indicates that the point is well separated from another cluster. And we have a silhouette score computation. So the silhouette coefficient for each point is given by this formula. So value of S lies between -1 and +1. S is approximately 1, so the point is well clustered. So it's as well fit inside some cluster, and also it's way apart from the different another different cluster. If S approximately 0, the point is near the boundary between the two clusters. And if S less than 0, that means the point is likely misclassified. A good clustering results should have silhouette scores close to +1 for almost most of points in our dataset, meaning that all points are much closer to their own cluster than the nearest foreign cluster. If many points have negative scores, it suggests that some clusters may be poorly defined or the number of clusters may need adjustment. Okay. In many real-world scenarios, we perform clustering on dataset where we already know the correct class labels, but we don't use them for the training, only for validation. This setup allows us to evaluate how well a clustering algorithm recovers the underlying structure of the data without direct supervision. If we assume that clusters should correspond of classes, this is a fundamental challenge because the number of clusters produced by algorithm may not match the number of actual classes, and the distribution of objects in the clusters may not perfectly align with the true labels. So how can we measure clustering quality in such cases? Instead of directly comparing clusters to their ground truth labels, as we made in classification problems, we should evaluate how well each individual object is grouped using a method called B-cubed, precision and recall. The core idea B-cubed precision and recall is B-cube evaluation is that for each object X, if we compare the cluster assigned to the object by the algorithm and the true cluster class of the object according to ground truth labels. So step one, define the sets. Some P is the set of objects in the same cluster as XE, and QE is the set of objects in the same ground truth class as XE. Yeah. So with this definition, we can now compute precision and recall for each object. No, we now talking about if we have for several objects know their ground truth. So now we have some. Yeah, it is just we want to know how good we have prediction. So step two, the computation of precision and recall. Precision, it's a fraction of objects in the same cluster as XE actually belong to X true class. So it's this metric evaluates how pure each cluster is. If a cluster consists mostly of objects from the same class, true class, its precision is high. If a cluster contains many mislabeled objects, its precision is low. Recall what fraction of objects in the true class and XE are correctly placed in the assigned classes. So recall evaluates how well each true class is captured by a single cluster. If true class is mostly concentrated in the single cluster, the recall is high. Otherwise, is low. And also we can count F1 score. It's a harmonic mean of precision and recall, balancing both metrics in the single score. So if precision and recall are high, the F1 score is high, meaning the clustering closely matching the ground truth. If either precision or recall is low, the F1 score drops, indicating poor clustering performance. Why does it matter? Unlikely classification, where each object is assigned a class labeled and compared directly to ground truth, clustering does not have predefined class labels. Instead, we must measure how well we discover classes aligned with the actual categories. If precision is high, but recall is low, this means that the algorithm creates many small pure clusters, splitting true cases in multiple parts. If recall is high, but precision is low, this means the algorithm groups multiple classes into one large cluster and failing to separate them correctly. And a high F1 score means that the clustering closely follows the true class structure. So this method of quality allows us quantify clustering performance objectively, even when the number of clusters differs from the number of true classes. Now let's talk about use all these previous ideas to understand how the most popular, well-known, and simplest clustering method, k-means, operates. K-means is optimization algorithm that minimizes the sum of squared intra-cluster distances. This means that each object should be as close as possible to its cluster center, mu. Yeah. Where ith is this one is cluster center, and ith is the cluster assignment for object xe. So we took some point, assigned to some cluster, and to its cluster center. So distance calculation and optimization, the distance is defined as the Euclidean distance. If we replace the Euclidean distance with another metric, we are efficiently solving a different problem, not standard k-means. The Lloyd algorithm is the standard optimization method for solving this problem in Rn, assuming that objects X and cluster centers are vector. Something wrong with the check, but I hope there is nothing here. So the main idea of method is the iterative repetition of two steps, assigning objects in the dataset to clusters and recalculating cluster centers. At the beginning of the algorithm, k random centers are chosen in the feature space. Each object in the dataset is assigned to the cluster. What center is the closest to the objects? Then the cluster centers are calculated as the arithmetic mean of the feature vectors of all objects that belong to that cluster. So, for example, the center of mass of the cluster. Once we update the cluster centers, the objects are reassigned to the clusters, and then we recalculate the centers again. This process continues until the cluster centers stop changing. So we just taking new centers, recalculating, got new centers, centers recalculating, and so on. The first question when selecting initial cluster centers is how to avoid placing centers in empty regions of the feature space when choosing centers from the sum random distribution. A basic solution is simply to choose some objects from the dataset as the center. So for example, we may take the center as some random point of the space, but otherwise we just taking the element as the center and calculating. The second potential issue is centers being placed too close together. In this case, their initial positions are likely to be far from the final cluster centers. To counter this, it's beneficial to choose centers that are maximum distant from each others on the whole space of dataset. So the first center is chosen randomly from, for example, uniform distribution or over the dataset points, and each next center is chosen from the probability distribution over the dataset points, where the probability is of selecting an object is proportional to the square of its distances from the nearest cluster center. So the modification of k-means that uses this heuristic of choosing initial centers is called k-means plus plus. Since the k-means method consists of repeating two steps until convergence, the justification for the using different metrics depends on whenever they break any of these steps. However, in the practice, nothing prevents using the methods without strict justification, so experimentation with different distances is possible. So k-means is just a little silly algorithm that can be modified in many, many ways. Yeah. Also, we have computing distances takes O big from D, where D is a feature space dimensionality. And we have some methods to speed up k-means. For example, we can reducing the feature space dimensionality beforehand using, for example, PCA or embeddings. We're going to talk about PCA a bit later in this lecture. This approach is especially effective because, for example, it's especially effective in the task clustering task, where k-means is applied to word embedding, and the benefits are faster execution and better interpretability of cluster results. A well-known example of using clustering for feature quantization is a bag of visual words method, and also directly searching for exact pixel matching fragments in the new images is impractical. Instead, the clustering enables a more generalized representation. Historically, k-means was the go-to method for this task, but today feature extraction happens automatically in deep learning models, not in any k-means modifications. If we need to provide the customer, so okay, for clusterization task, I think it's maybe clear. For semi-supervised learning, we have labeled data only for our evaluation, and the difference between k-means for unsupervised and k-means for semi-supervised learning is just here we're gonna took all the centers, but here we need to took only our unlabeled centers, because for label is, well, we know which labels they have. So pure initialization splitting a large clusters on this image. Imagine we have for first image, we have a data set with three well-defined clusters. Due to unlikely initialization, a centroid is placed inside an unrelated clusters. As a result, one large red cluster fails to form collectively, like here, and gets split in half. Meanwhile, a smaller cluster gets absorbed into the wrong group. What happened? The initial centroid placed was too close to an existing cluster because we took, yeah, it's difficult to see, but we took so close points in one cluster. But we thought that it will be two clusters. And instead of converging to the correct three clusters, the algorithm incorrectly merged two clusters and split another. Solution: just use k-means plus because it improves our centroid selection. Another example of unsuccessful k-means clustering is wrong cluster orientation. For example, vertical versus horizontal. Let's consider a case where the true structure consists of three vertical clusters. However, due to poor initialization, all centroids start in the same clusters. Instead of forming three vertical clusters, the algorithm slices them into three horizontal clusters. Now, no further iteration will fix that because the k-means is stuck in a local minimum. Why does this happen? K-means relies on initial centroid placement, but initialization can lead incorrect partitions. Voronoi partitioning, which k-means naturally follows, is not flexible enough to adjust to non-spherical cluster shapes. So, because distance between different like true clusters is so big, is much bigger than distance now between centroids, all new clusters will be here only in this cluster. So it's never, we never never took centroids from the true clusters. And what else? So, yeah, for example, we have several different clusters in several different shapes. Like k-means work perfectly with clusters that can be in one spherical cluster. For example, here we can have two circles. No one can be placed inside one sphere, not touching another cluster. And that means k-means will be fail on this task. Yeah, another. So let's move on. An algorithm that solves the problem of spherical clusters. So here we can have issue. K-means never done this style clusters. Here is an algorithm that doesn't make any assumptions about cluster shapes. It is a well-known algorithm, not new, but still widely used and loved. For example, I used it in my coursework in previous university on the third course. Moreover, it's quite fast, making it suitable for clustering large data sets, and it is also very simple to understand. It's based on the concept of neighborhood. So we have some neighborhood definitions. A neighborhood is a set of objects that are located within a distance of no more than some epsilon from the given object X. Each object in our data set or space can belong to the one of three types. Let's introduce them. It's a core object. It has a dense neighborhood, means it's epsilon minus it's epsilon where epsilon neighborhood contains at least m objects. This introduces two parameters, epsilon and some m, and there will be no other parameters. The resulting clustering will depend entirely on these two parameters. This method is also good because it's doesn't require specifying the number of clusters in advance. The number of clusters is determined dynamically based on epsilon and m. In contrast, k-means requires specifying like k, because k-means, so we're gonna give it to algorithm k clusters for clusterization. Then border object. It's not a core object, but it is within the neighborhood of core object, and noise object or any outliners. It's neither a core object nor a border object. So how the algorithm works step by step. We start with the arbitrary points. If it has a dense neighborhood, for example, it satisfies the core object condition, then we expand the cluster. Like here, we have several points, and they got one cluster. So expand the cluster by considering all points within it. For each of these points, we also build its own neighborhood, and the process continues until we reach the outline boundary of dense region. So here we got several classes, and we classified all points of our dataset in those three types: core, border, and noise. So these are core, this is border, and these four red points are just noise. Here we can make some analogy. For example, the forest. It's one of the best ways to visualize this algorithm is to imagine a forest. A dense forest represents a cluster. A single tree represents a data point. If you're inside a forest, you look around and you see many trees in your neighborhood. That means you are in the core object. As you walk through the forest, you continue expanding the cluster, moving from one dense area to another. And eventually, you reach the forest age, trees become less dense, and suddenly you see half trees, half open field. You are at a border point. Yeah, that means you are at a border point. If a tree is standing alone in the open field, far away from the other trees, that means it is an outliner or a noise. So the algorithm walks through the entire space like a person exploring the forest. Let's now formally, yeah, I'll make it better for slides because we have some written sense, but we can describe DBSCAN for pseudocode. At the beginning, all points are unmarked. We will assign them to a cluster during execution. So in input, we got dataset XL and parameter epsilon and m. And for output, we want partitioning into clusters and noise points. So step-by-step explanation. All point stars like enabled. We iterate through each point x in the dataset. If x is at least m neighbors within distance epsilon, a new cluster is created. All points within x neighbored are added to that new cluster. And the search continues recursively to expand this cluster. So we took point, create cluster, then all the neighbors are added to this cluster, and then our cluster gonna grow. If x has fewer than m neighbors, it's marked as a noise, just like on this example. For example, here we made m neighbors, for example, 3 at least. So these points have only one neighbor, so they're never gonna be in one cluster. They're always gonna be noise as well. We have m more than one. So the process continues until all points are assigned to a cluster or marked as noise. Yeah, it's clearly to see here our analogy with the forest. Advantages and disadvantages of DBSCAN. It doesn't assume cluster as it doesn't assume the clusters are spherical, unlike k-means. It's clear. Also automatically determines the number of clusters, so it's no need to know k for our number of clusters. Also, it effectively detects noise in our dataset and works well with elongated clusters and clusters with bridges. For example, for these clusters, k-means may start somewhere here, create this cluster, then this cluster, and this cluster. While DBSCAN gonna go through all these clusters and create one big cluster here and one smaller here. No. Yeah. Now disadvantages. Computation complexity is squared in the worst case, but we have some improvement to n log n using L log n, L log L. Some using heuristics and efficient spatial indexing. We don't want to know about it now. Also, it struggles in high-dimensional spaces as a distance-based method degrade and sensitive to parameter selection. For example, if we choose like M1, so it will be like clusters. Instead, if any another bigger M, it never gonna be some cluster. Yeah. Now let's take a closer look to border points in DBSCAN to see we can see small colored points labeled as border points. Yeah, they are border points, but they do not form the exact boundary. In fact, many other points at the edge of cluster could also be considered border points. but it still so happened that these specific points were labeled as such. Why it's important? The fact that some points at the edge were labeled as border points while other were not, doesn't imply a strict boundary. Another point nearby could have been a border point, but it wasn't assigned as one. This is simply due to the order of processing and how the cluster expands. Yeah. I think we're going to go to the next theme. It's hierarchical clustering algorithms, also known as taxonomy methods, do not just partition the dataset into not overlapping clusters, but rather create the dataset into non-overlapping clusters, just don't partition the dataset into not overlapping classes, but rather create a nested hierarchy of partitions. So the result of this clustering is usually represents as a tree-like structure called a dendrogram. We're going to talk about it later. A classic example of such a tree is a hierarchical classification of animals and plants in biology. There are two main types of clustering algorithms: is divisive or top-down methods. So this algorithm starts then with the entire dataset as one cluster and then split it in the smaller, and agglomerative, bottom-up. So we're gonna take each element as one different cluster and then gonna set them and pair in bigger clusters, and then goes, and we created one big cluster with all elements of our dataset. So how agglomerative clustering works? Each object is initially treated as a separate cluster. Then for a single element cluster, the distance function is naturally defined as the distance between two objects. For example, here we have R big R or rho. They merge the closest clusters on each iteration until only one large cluster remains, or until a stopping criterion is met. For example, we want to take no less than 3 clusters, so then there are left only 3 clusters. Our algorithm gonna stop. For single, at each iteration, each iteration, the two closest clusters, U and V, are merged into new cluster, W. The distance between the new cluster and any other cluster, S, is then calculated based on their distances. So RUS and RVS, which have already been computed. And we got this formula RWS is alpha URUS plus alpha VRVS plus beta RUV plus some gamma, and the absolute of this difference. Here alpha, beta, gamma are just some parameters. And this formula is very useful for all agglomerative hierarchical clustering. So it's many theorems that proving that is formula work. And we don't want to do this now, but just trust me. For semi-supervised learning, here we're gonna create when we finding the pairs of clusters with a minimal distance between them, we provide that the set U and V contains no object with different labels. So if we have different labels, we skip it. If we have the same labels, when we can union these two sets. In practice, several different methods can be used to compute cluster-to-cluster distance RV in our Lens-Williams formula in our clusterization. Each of these distance measures corresponds to a specific choice of parameters in the Lens-Williams formula. For example, we can single linkage. It's just nearest neighbor distance between classes. So here's the image. This nearest, we counted distance. So the distance between if with W and this is S is gonna be just minimum distance between these 2 points. Otherwise, we can use complete linkage or farthest neighbor distance. It's distance between two clusters is defined like largest distance between any 2 points in their clusters. Yeah. Third, gonna be group average distance or mid distance or average linkage. Is the distance between clusters is defined as the average of all pairwise distance between points in the 2 clusters. So it's pretty clear. We got for this formula these parameters. Also, we have centroid distance. We're going to calculate some centroid point for each cluster. For example, if this cluster have only 3 points, then centroid going to be somewhere here. For this cluster, somewhere here. And then we just measure the distance between these 2 points as in the formula. And we got these parameters. There are many theorems that proves that for each corresponding formula, there are these parameters, just trust it. We don't need to prove it. We just need to understand that there are several distances for Lens-Williams formula. The most powerful distance, which if you want to use these hierarchical methods, you want to prefer use the words distance. In simple ways, this method minimizes the variance of distance within clusters of each step. So it's like centroid distance, but it have some normalization depending of the size of those 2 clusters, W and S, and have corresponding parameters. So here we have different distances, have different our methods step-by-step solution, and have different dendrograms. So for example, when we want to calculate nearest neighbor distance, on first step, between 0.3 and 0.6, there are nearest distance. Here we can see 3 and 6. Nearest between any of them. And then we collect them into one cluster. On the second iteration, we have cluster this one, cluster this one, cluster this one, cluster this one, and these 2 points are in the same cluster. So we're going to talk about only these clusters. On the second iteration, we union 2 and 5. On the third iteration, we have the smallest distance between 2 and 3. so between clusters 1 and 2, and we union them into one big cluster. And then we just add 1 and 4 on the further iterations. It's a bit the same for the farthest neighbor distance, also for group average distance and for worst distance. The main idea that the different distances have the different dendrograms. And as you can see, the word distance, we have the prettiest one. So because it have like less different distances between those clusters, because we can see the distance difference between one and cluster that include 3, 6, 4, 2, 5. It's just a little, while for worst distance it's way bigger, and like it's just simpler and better. Yeah. And dendrogram. Their monotonically property allows us to represent the clustering process as the special type, as we've seen before on the previous slides, as a special type of graphs called a dendrogram. On the vertical axis, objects are plotted, and on, here we can different. Here are objects, and here are their distances. Yeah, here the same. Distances, objects. It's not difficult to prove that if a cluster satisfies to monotonically property, then the dendrogram can be conducted without self-intersections. At the same time, any cluster from the set is represented as a continuous sequence of points on the vertical axis. If the clustering process is not monotonical, it's when the distances between classes only grows and never go less. The dendrogram allows us to present cluster structure in the form of flat graphs, regardless of the dimensionality of the original space. Other methods for two-dimensional visualization is multi-dimensional that exist, such as multi-dimensional scaling or coherent maps, but it's too difficult for us. So maybe you're going to meet it in the university. But they introduced artificial distortions, which was impact is quite difficult to access. Yeah, here we have some properties of distances. Is monotonical. Let R is distance between the closest clusters on the teeth step. So it's on the second, third, and else. The distance function R is said to have a monotonical property if at each merging step, the distance between the merged clusters only increases and never decreases. It turns out that not every combination of the coefficient in the Lens-Williams formula leads to monotonical clustering. Okay. And there is Milligan's theorem that clustering is monotonical if the following condition holds, depending on the coefficients in the Lens-Williams formula. And we can just look at those coefficients for all distances and see that distance for centroid is not monotonical when all others are monotonic. Yeah, wide distance differs from it only by a multiplicative coefficient factor, which makes it also monotonical. Some distances measures exhibit the property of expansion, as the cluster grows larger, its distance to other cluster increases, as if the space around the cluster is expanding. So, for example, difference between clusters increasing, and here is not. So yeah, it is contractive distance and expansive distance when we have less and more. Advantages and disadvantages of agglomerative clustering. There are no definitive answer to the question of which clustering algorithm is the best. Each of the distances mentioned above has its own drawbacks, and it's not suitable for all tasks. So, but the nearest neighbor method exhibit the chaining effect, where objects closest to the boundary of a cluster continue to be added regardless of the cluster shape. In some cases, this leads to cluster growing tangles. Also, depending on the task, this property can be either useful or problematic. War's method has been found to be the best based on just experimental comparison on the representative set of model tasks. And it's often considered the most intuitive approach for the better taxonomy. As I remember, the best no, I don't remember the best coefficients for the BART methods for almost all tasks, but you can just Google it and find it. PCA, or Principal Component Analysis. It's generally used for visualizing the strongest trends in the dataset or between groups of datasets. These groups can be, for example, sick of healthy group generated using cluster methods, like k-means clustering. Below, an example of PCA is given when clustering analyzing have been performed using k-means clustering. When performing k-means clustering and clustering analysis in general, it is desirable to be able to display the observations and clusters in a standard two-dimensional plot with one variable on each axis. The number of variable is, however, often much larger than 2 and far too many to represent visually. So PCA is a feature transforming technique used to reduce the dimensionality of number data while preserving as much variance as possible. So, for example, we have some original numerical features. We have new numerical features with less dimensionality. And after we have these two like matrices with all features that was before and we want to after, it's going to be some matrix magic with some difficult theorems with some matrix transformations. So we want to learn not only the like resulting representation of our dataset, but also our transforming matrix. Yeah, it is maybe seems a bit difficult, but it's just some matrix transformations that transform our dataset in less dimensional. A PCA plot is a lot like a simple scatter plot with the two first principal components on the x and y axis. The PC are, as mentioned above, artificial variables that explain as much as of the variation in the data as possible. And these artificial variables don't have any units, and thus the x and y's values themselves are not important, but rather their values relation to each other. On a plot, on PCA plot, you will very often see a percentage of each axis, like here, dim2 and dim1 have their percentages. This indicates how much of the variation that is explained by each PC. In the example below here, principal component 1, dim1, explains 35.9% of the variation in the data. Principal component second, on the y-axis explain a bit more than 5% of the variations in the data. On the PC plot, data points belonging to different clusters will often have different colors or different shapes. For example, you might color males and females in the blue and green and represent whether they are cases or controls as circles and squares, such that a female control subject would be represented as a green square. This makes it possible to identify the groups of study on the plot and see if they form distinct clustering. The group could just as well overlap on the plot. Small overlaps indicate that groups are slightly similar in the data and that we are not able to distinguish between groups in the extreme cases. Large or complete overlaps indicates that we don't see any difference between groups in the data at all. As mentioned before, the task of visualization consists of mapping objects into 2 or 3-dimensional spaces. Like in PCA, we want to reduce the dimensionality to visualize our data, and we want to visualize it to 2D or 3D. By preserving relationships, one usually means maintaining the proximity of pairwise distances of the original and the new spaces. Thus, in multi-dimensional scaling MDS method, the squared deviations between the original and new pairwise distance are minimized, like in this formula, where X are the original objects and Z is objects in their low-dimensional projection. Let's focus on the 2 case features of this approach. First one is the original objects don't have to belong the Euclidean space. It's sufficient to be able to compute distances between them. This allows us to visualize even complex objects such as text sequences. Also, object projection are determined directly without any parametric dependency between them and the original object representation. Because of this, it's difficult to incorporate new data into the visualization. However, this is not always necessary. After all, we often just want to draw object and look at them. If we don't need to display new test data, it's preferable to use dimensionality reduction methods that transform object using a certain model. One of the most popular visualization methods today is t-distributed stochastic neighbor embedding, t-SNE, which addresses several case problem of multidimensional scaling. To begin with, note that exact preservation of distances is not necessary after projection. It's sufficient to preserve proportion. For example, if rho x1, x2 equals alpha rho x1, x3, that means rho z1, z2, where z is representation of x, equals alpha rho z1, z3. Then in U space, so all space relation and U space relation. A normal distribution is used to measure similarity between objects in the original spaces with this formula. We normalize these similarities so that we obtain a distribution vector of distances from object X to all other objects. These values are not symmetric. which can introduce additional difficulties in further computations. To resolve that, we symmetrize them like here, and thanks for this symmetrical approach, it's impossible for the situation to arise in which for some distant object xe all similarities p are close to 0. It can be shown that the condition more than, yeah, I didn't draw it here, by the way. Now let's move on to measure similarity in the new low-dimensional space. It's known that in high-dimensional spaces, objects can be arranged in such a ways that their pairwise distance are closed. However, preserving these properties in a low-dimensional space is unlikely to be feasible. Therefore, they will measure the similarity between objects using the Cauchy distribution, which has heavy details and doesn't have any penalized increasing distance between objects. And now we can measure distance between objects both in the original spaces in the new space. And all this remains is to define the projection error functional. Also, we can measure there using KL divergence or Kullback-Leibler divergence, which is commonly used to measure distance between different probability distributions. This optimization problem can, as always, be solved using any stochastic gradient descent. So that's all for today for clustering. The main parts that you may use in the future is DBSCAN and k-means exist, and the DBSCAN is almost better. For any hierarchical clustering, it's better to use worst distance. And for visualization, there's also use some unsupervised methods like PCA and t-SNE. Yep. That's all for today. Thank you.